Hello, can you please confirm that you can see the presentation and hear me? Hello,
Yes, sir.
thank you, thank you. Okay, so what we shall do is that we shall briefly go back to this last point where we ended the previous lecture, which was last Friday. Um, that prior to that, we had established that the curl of the electric field is the negative time-dependent time derivative of the magnetic field. So this is actually Faraday's law as established mathematically in the language of differential equations by Maxwell. Um, Remember, our task will ultimately be to establish the four Maxwell equations. So we have done two already. We have gone through two already. One is that the divergence of E is equal to rho by epsilon naught, and the divergence of B is equal to zero. So these two equations were the ones that we had taken up in electro and magnetostatics. But now we have to bring in dynamics, which means explicit variation in time. And we have seen one such equation already, namely the curl equation. Curl of E is equal to minus del del T of B. So now we shall have to look at the curl of the magnetic field. So in electro and magnetostatics, the curl of the magnetic field is equal to mu naught into J, where J is the cross-sectional current density. So you do not see any appearance of time in this equation. You do not see something like a t here, be it a part of an operator as in del del t or just as a function. T does not appear explicitly over here. So we shall now have to see how t might be introduced. And this is a particularly important discussion, Maxwell's correction of Ampere's equation. So let us see how. So when you have a steady condition, then divergence of J is equal to zero. As we have we can see over here, curl of B is equal to mu naught J. Divergence of the curl of a vector function is zero. Therefore, divergence of mu naught J is equal to zero. Mu naught is a non-zero constant, but these two multiplied will give you zero. Therefore, it can only mean that the divergence of J is equal to zero. So which is a solenoidal field. Fine. Now we shall see some time-dependent behavior. This was the point where we ended. Let us resume that discussion. So you have something, a volume in space that contains charges. At any given point of time, t, the amount of charge. I'm sorry, excuse me. Just a minute. Can you please excuse me? Yes. Hello. I'm sorry. I hope you are able to. I mean, you're there, able to see the presentation. Thank you. So here, so this is some kind of a sponge, just as you have water filling up a sponge. The water example is an important analogy, although instead of water molecules, as in H2O, we shall be talking about charges. Let's say some kind of charge, positive, negative, whatever. So at any given point of time, T, Q amount of charge is contained. Now, through this region, through the enclosing surface of this region, charges are seeping out, charges are leaking out. Okay, so G is the cross-sectional current density, and dimensionally, it is charge per unit time per unit area. That is G. Charge per unit time is current, per unit area is current per area cross-sectional current density. That is J, dimensional. Let us just discuss this thing in simple dimensional terms. Now, if the area through which this cross-sectional current is passing is dA, then the amount of charge per unit time flowing through that area dA will be J into dA, but we have to be a little careful. dA is an area vector element. J is also a vector, so we have to take the dot product of that. Charge per unit time, of course, is going to be a scalar. So charge is leaking out of this area dA in unit time as per this formula. The amount of charge that is leaking out through the area dA is J dot dA. So what is the total charge leaking out through the entire surface? That is the next question. And so basically what you have to be, I mean, what you have actually found out is the flux, the current flux, E dot, just as you have it in E dot dA or B dot dA. E dot dA is what you see in Gauss's theorem. I'm sorry, not Gauss's theorem, Gauss's law of electrostatics in the integral form. And B dot dA will be zero because of the Gauss divergence theorem. Here, it is something like that. It's the current flux, charge per unit time leaking out through the area dA area element. So the total amount of charge leaking out through the full enclosing surface will be the surface integral of J dot dA. Okay. Now, that is the charge per unit time leaking out through the entire surface. Now, what is the charge per unit time leaking out through the entire surface? The rate, now you follow the logical equivalence of this statement, minus d dt of q. The rate at which charges are leaking out is equal to the rate at which charges are being depleted inside. Of course it is. Charge is a conserved quantity. So in 1 second, in time dt, if dq amount of charge has leaked out, then the charge loss inside would be minus dq. So, and so minus q is the amount of charge contained. dq will be negative. Well, I mean, dq is the rate at which charges are, dq dt is the rate at which charges are being lost inside. I'm sorry, I just made a slightly mistaken statement. dq dt is the rate at which charges are being lost inside. So the rate at which charges are being lost inside is equal to, numerically equal to the rate at which charges are coming out. So that will be minus d dt of q. So that is what it is. So that minus sign indicates here that dq is a negative quantity. At a point of time t, you have q amount of charge. After a little time elapse of dt, the amount of charge contained in this space will be less than what you started with. So dq will be negative in this volume. But that negative will be equal to the positive contribution to the charge going outside the volume. So minus dq here. So minus dq dt. Okay, once you have established this thing, thereafter it is just, so this is the only physical argument that you have. Thereafter, it's just some mathematical trickery that you have to employ. And this is a familiar formula for you. Find the charge contained in a certain volume. So Q is equal to charge density d tau volume integral. Okay. Now, Q is a function of T, but charge density is a function of the spatial coordinates as well as time. Just think of the air contained in your room. The air contained in your room is the total amount of air that is contained. So that doesn't depend on X, Y, Z, individual. You can't say that this is the amount of air contained at this point or at this point. You can only talk about the air density. If your room is very tall, very high, for instance, you can say that, there's more air per unit volume close to the floor than close to the ceiling. But I mean, you have to have an extremely tall room for that. I mean, air density reduces as you go up. So charge density is a function of the spatial coordinates, X, Y, Z, and T. And in fact, in your tutorial problems, I think it was tutorial 3 or whatever, where you had worked with rho given as a function of the spatial coordinates, X, Y, Z, or R theta phi, or S phi Z. Here we are just adding another variable, independent variable, time. Why? Because now this is a situation whereby you have dynamics. Charges are leaving this system. And if they're leaving this system, then the total amount of charge contained within the system is reducing. And since the volume is constant, if the charge is reducing, then the charge density will also be reducing. So basically, this is just what happens when you have a water sponge. You fill in the sponge with water, you dip your sponge, a dry sponge, in a bucket full of water. It'll immediately get soaked with water. And then when you bring the sponge out and squeeze it, the water will squirt out of the sponge. So instead of water, we are now talking about current charge. Incidentally, you notice that the word current is also used in the context of water flow. you will say that the river Ganga has got a very strong current in the Himalayas, which means that it flows very fast. Okay, I mean, amount of water flowing through unit area, through a unit time window is much more than what happens down in the plains. Anyway, so what we will do now is a very simple thing. We will just apply the Gauss divergence theorem to this thing. Let us see. So dq dt is equal to ddt of q is replaced by rho d tau with a volume integral. Thereafter, we exchange, in the last class we discussed in the context of Faraday. Here, we discussed how you can exchange the integral sign and the derivative. They mean they don't lead to any different outcomes. So you exchange the integral and the derivative, except that q was just a function of t. Therefore, when you took the derivative of q, you were able to write a full derivative ddt. But rho is a function of x, y, z, and t. Therefore, when you want to take the derivative of the charge density rho, you have to be a little careful. You will have to write del t to indicate that you are only interested in taking the variation of rho as a function of time and nothing else. So that is why you write del t of rho is equal to d tau. Okay, so j dot dA, surface integral, is equal to minus dq dt. Put a minus here and you put a minus here. And then you put it over there. So dq dt with the minus sign is replaced by volume integral minus del rho del t is d tau. That is, well, I hope you have understood this thing. dq dt is replaced by this with a minus sign that goes inside the integral. Okay, so you have a surface area integral and you have got a volume integral. But there is a way to connect a volume integral with a surface integral, and that is the Gauss divergence theorem. So divergence of j d tau, volume integral, is equal to this thing, closed surface flux of the current, and that's equal to this thing. So this and this, they are coming from the Gauss divergence theorem, whereas this and this are coming from the physical argument that we have held here. Okay, so it's part physics and part mathematics put together. Next is that as soon as you have a way of connecting a surface integral to a volume integral, the next task that you can do is to write divergence of j, and here you have got d tau, here you've got d tau, you've got a volume integral, you've got a volume integral over here. So divergence of j is equal to minus del t over rho. So here we have a problem. Divergence of j is not equal to 0. And yet, when we take Ampere's equation, divergence of j must be equal to 0, because this has to be curl of b is equal to mu naught j, fine. But then the divergence of the curl of b will be 0 all the time. It's a mathematical theorem. There's nothing physical about it. Divergence of curl of the vector function is equal to 0. Okay, that's very good. But then that will also lead to this conclusion that divergence of j is equal to 0. But now we see through this argument, and there's nothing wrong with what we have done over here, current flux as a function of time with explicit time dependence, we see that divergence of j is not equal to 0, it is minus del t of rho. So there's a conflict with Ampere's law. And so this is what Maxwell resolved. Note the title of this discussion, Maxwell's correction of Ampere's equation. It is a very important discovery. I mean, it's changed the course of history, you can say. Okay, let's see how. But before that, I'd just like to touch upon something. This equation is known as the equation of continuity. Divergence of j is equal to minus del t over rho. What is rho and what is j? Rho is charge density and j is charge, but just you follow this thing very carefully. We may need it on some other occasion, if not in electromagnetic theory. Rho is charge density, and this is charge per unit time per unit area. J is current per unit area, current flow per unit area. Current is charge per unit time. Charge per unit time per unit area. This is charge per volume. So if you instead replace the charge by other things, let's call it X, x per volume, and this will be x per unit area per unit time. You can replace anything with that x. You can replace that x with anything. It's the other way around. Sorry. Here we are calling it charge. You can replace that x with matter. Matter per volume and matter flowing out per unit area per unit time. What kind of matter? Fluid matter, as in water. Water per volume and water per unit time per unit area, or air per volume, or and air per unit area per unit time. All sorts of things. Why am I talking about air and water? Because if you were a mechanical engineering student, you would have had to study fluid mechanics, and this is a very important equation in fluid mechanics, except that here we are talking about electromagnetic theory, but I have given you so much fluid analogy. I've talked about water, I've talked about air, all these things. Sponge full of water. Instead of a sponge full of water, we just have a sponge full of charges. So this is a very general equation of continuity. Continuity, what do you mean by continuity over here? That things are continuously flowing out and things are getting depleted. Things are continuously moving through an area of cross-sectional area. So that is what it is. It's an extremely important equation in fluid mechanics. And if you were a mechanical engineer, you would have had to study hydraulics and all that stuff. And so this equation would have been like, the thing that you have at the back of your hand all the time. Okay, so anyway, I will not labor that point any longer, just to motivate aside something. Just remember, this is x per volume and this is x per time per area. And here our x is charge. That is what it is. In other cases, it can be any other thing. Okay, now what we have to do is we have got a divergence over here and we've got a time derivative over here. We need to kind of substitute this time derivative with something. With another divergence. So we are looking at rho here. And there is indeed, rho can be connected to the divergence of a function, an electromagnetic vector function. What is it? Gauss's law of electrostatics in differential form. Divergence of E is equal to rho by epsilon naught. You take the derivative of this equation. Del T of rho is equal to epsilon naught into del T of divergence of E. Okay. I think you will know what I have done hereafter. But anyway, I've done it in detail, making use of Cartesian coordinates. What is divergence of E? If E has got three components, Ex, Ey, Ez, I'm writing del del x of Ex plus del del y of Ey plus del del z of Ez. Okay, and I have discussed this point earlier also. Whatever be the order of derivative when you're talking about a second order derivative, it doesn't matter. You just exchange the derivatives. So first we have taken a spatial derivative in three coordinates, then we are taking a time derivative. So del del x, del del t of E plus del del y, del del t of Ey plus del del z, del del t of Ez. That is how we have taken. Okay, and then we write it, close it, or summarize it again in the form of vector differential operators. This is what we have done. Del del t of Ex, del del t of Ey, del del t of Ez. All of these things, and del del x, del del y, and del del z, we can write it, exchange time and space derivatives. And what we had, del del t of divergence of E could be written as divergence of the del del t of E into epsilon naught. So now we replace the del rho del t in this equation, del rho del t with the minus sign over here, with this thing on the right hand side with the minus sign. I put a minus here and I put a minus here. And this is what we have. Divergence of J is equal to minus del del t of rho. This is what Maxwell found using the equation of continuity. And then we have got my del rho del t is equal to this thing. So we put a minus here and write it like this. Epsilon naught divergence of del t of E. Then we now see that there is a divergence here and a divergence here. So we take this thing with a minus sign to the right, it becomes plus. We take the epsilon naught inside. So divergence of J plus divergence of epsilon naught del t of E. Epsilon naught being a constant, it can very well go inside the differential operator, is equal to 0. So you have a common divergence. So divergence of J plus epsilon naught del t of E is equal to 0. Now comes something very important. Uh, Here you find that divergence of J is equal to 0 when you have curl of B is equal to mu naught into J. Follow Maxwell's argument now. The math part is over. So we had a bit of physics here. Now we have a bit of mathematics over here. And now we have got the exercise of some imagination and highly educated guesswork. What did Maxwell do? There's no derivation going on here. Ampere's equation will say that divergence of J is equal to 0. Fine. Now Maxwell realizes that when you, so this is in under conditions of steadiness, you have got a steady current, divergence of J is equal to 0. Now current is flowing out of this region, charges are flowing out of this region in a current. But then as charges are getting depleted, the amount of current or amount of charge that will flow out in unit time will also change. So here we are talking about a current that is no longer fixed in time. It is varying in time. In such a situation, with all this workout, what Maxwell was able to show that divergence of J is not equal to 0. Indeed, it should not be, because charges are now flowing unsteadily, not steadily. Therefore, charge density will become non-zero. The derivative of charge density will become non-zero. Had it been steady, rho would not have had any time dependence. It would have been constant in time, and this derivative would have been 0. But now Maxwell is showing that divergence of J is not equal to 0. So what is equal to 0? Maxwell showed that it is not divergence of J that is equal to 0, but divergence of J plus epsilon naught del del T of the electric field is equal to 0. If that is so, then the next conclusion is that J plus epsilon naught del del T is the conserved solenoidal cross-sectional current density. Here you have got J as the conserved current density, solenoidal field, right? Steady current. But when you bring in time variation, it is not divergence of J that is equal to 0. Therefore, the conclusion is that it is divergence of J plus this extra bit that is equal to 0. And that extra bit is an explicit function of time. And so what you have, you notice that if the electric field were to be steady, that is to say, did not have any time variation, then del del T of the electric field would have been 0, and you would have had the old result. So this is a great leap of faith. What Maxwell did was, there's the mathematical proof of this thing. He just said that in under explicit time variation, if this is the cross-sectional current density, then curl of B is equal to mu naught J has to be replaced by curl of B is equal to mu naught J plus this thing. So this is Maxwell's correction to Ampere's equation. This is one great idea of human history. I mean, we will see how. Maxwell gave this, so this is the cross-sectional current density, normal current, normal flow of charge. And here Maxwell called this extra bit, epsilon naught del del T of E, he called this the displacement current, subscript D, D as in displacement, JD. So in shorthand, you will have curl of B is equal to mu naught J plus JD, where JD is epsilon naught del del T of E. So with this, now we have the four Maxwell equations. What did I tell you about the four Maxwell equations? That they are just two vector differential operators on two vector fields. The two vector fields are the electric field and the magnetic field, E and B. And the two vector differential operators are divergence and curl. Divergence of E is equal to rho by epsilon naught. We had this thing earlier when we talked about electrostatics and magnetostatics. Divergence of B is equal to 0. We discussed this earlier again when we talked about electrostatics and magnetostatics. When we talked about electrostatics, now you note please, when we talked about electrostatics, we said curl of E is equal to 0. E as in, let us say, the static Coulomb field, a fixed charge in space. So the curl of the electric field arising due to that fixed charge in space would have been equal to 0. But now we are talking about electrodynamics, as in the title of your textbook, Introduction to Electrodynamics. Dynamics as in things are changing in time. So that's why I've written this word next to it. Minus del del T of B, explicit appearance of time. So this is Faraday's law. And then the last part, in magnetostatics, curl of B would have been equal to mu naught J. But if you bring in dynamics, this is the extra bit that Maxwell introduced, mu naught epsilon naught del del T of E. So mu naught into epsilon naught del del T of E. So if I were to give names to this thing, let me just go through the list once again. Divergence of E is equal to rho by epsilon naught. Fine. This is Gauss's law of electrostatics. It comes from Coulomb's law. It captures everything. If Coulomb's law had not been there, then you would not have got this thing. So this is actually the consequence of Coulomb's law of electrostatic force. So divergence of E is equal to rho by epsilon naught. Divergence of B is equal to 0. It has got nobody's name, no name of no person, but the consequence of this equation is that there can be no magnetic monopoles. What do I mean by a monopole? A single point, which can either be a source or a sink. If divergence of a vector field is positive, then there is that vector field has a source. If divergence of the vector field is negative, then that vector field is going towards a sink. If a certain vector field has got zero divergence, as you have over here in this equation, then the field has neither a source nor a sink. It'll just keep going round and round. On a circular path, there is no starting point, natural starting point, there is no ending point. Whatever you define as your starting point becomes the starting point. Very simple. So that is what it is. And as such, there can be, and this mathematical statement leads to the fact that you cannot have magnetic monopoles. You can have isolated charges. You can have a positive charge and a negative charge taken apart from each other, isolated in space. But in case of magnetism, you cannot have that. This is Gauss packaging Coulomb in a language of differential equation. This is Faraday taking both left and right hand sides. This equation, curl of B is equal to mu naught J. Only up to that point is ampere. And then curl of B is equal to mu naught J plus this extra bit is Maxwell's correction. So this equation has got Coulomb and Gauss. Nobody's name is associated with this thing. This equation has got Faraday, and this equation has got Ampere and Maxwell. So those are the four Maxwell equations. For all practical purposes, we can say that this is the end of our quest, because all of electrodynamics, if you were to be an electrical engineer, all of electrical engineering is just applying these four equations in some way or the other, some form or the other. You are just studying electric field and magnetic field, what to do with that, this, etc. Everything is packaged. All of it, just like all of classical mechanics, all of mechanics is packaged in the three laws of Newton: first law, second law, third law. Similarly, all of electromagnetic theory is packaged in these four equations. There is one last point I'd like to make before moving on, is that in free space meaning a space that does not contain any charge. If a space doesn't contain any charge, it will also not contain any current. Nevertheless, vacuum, free space as it is, can contain electric field and magnetic field. Consider the sun. The sun is a charged spherical fluid object and fluid sphere. So the movement of the charges inside that fluid sphere gives rise to powerful magnetic field. It also, the charges themselves will give rise to electric field. Everything is fine. But all the radiation that is generated will come through space, which is empty. So the electric and the magnetic field of the sun is not confined to the charged region of the sun alone. They leave the sun and they move forward all the way up to infinity. So empty space, as in vacuum, may not contain charges and therefore will not contain current either, but they can very well contain electric and magnetic field. In that case, you will have something interesting over here. Divergence of E will be equal to 0. Rho by epsilon rho is equal to 0. So rho by epsilon naught will be equal to 0. Divergence of E is equal to 0. Divergence of B is equal to 0. Curl of E will be equal to minus del del T of B. And curl of B will be equal to, this part will vanish again. J will be equal to 0. So curl of B will be equal to epsilon naught mu naught del del T of E. And this thing will lead to the concept of light being an electromagnetic wave. We shall show that thing later. But for the time being, let us look at a little something extra. This is from David Griffiths, section 5.4.2. Magnetostatic boundary conditions. Just like, charges on a conductor and all that stuff when we talked about electrostatic boundary condition. Here we shall talk about magnetostatic boundary conditions. Let us see how. Divergence of B is equal to 0. Fine. And so we apply the Gauss divergence theorem, which says divergence of B d tau, taking the volume integral, is equal to the closed surface flux of the magnetic field. Okay. So if divergence of B is equal to 0, then this whole thing is equal to 0. B dot dA, the closed surface integral, is also equal to 0. Okay, fine. Just a minute. Next thing is that, what do I mean by the closed surface flux is equal to 0? Whatever field lines enter a certain region in space or through a certain surface, the same number of field lines will also exit that surface. Here we have a situation like that here's a sheet. Now we are talking about magnetic field, so we can't just talk about static charges. We'll have to talk about charges flowing on this sheet. So let's say a copper sheet, and current is flowing along this copper sheet. So we have taken a small pillbox. Half of the pillbox, this dotted rectangle is a section of this copper sheet. Half of the pillbox is sticking above the sheet and half of it below. Okay. A magnetic field line has come from some great distance, wherever. Although I've drawn a straight line, it would be safe for you to think of magnetic field lines as not straight. They can be, but in general, they are not. So here's a magnetic field line passing through. In fact, very soon we shall be talking about a straight magnetic field line. So here is this arrow going through. It's come from a great distance, and it's intersecting this copper sheet or piercing this copper sheet from below and passing above. We draw two components, a perpendicular component this way, B perpendicular above, and then extended below with the arrow pointing inwards is B perpendicular below. And parallel to this plane, you'll have B parallel, that is the horizontal component. Okay, so make this pillbox as thin as possible, thin pillbox. So the field lines, if you just look at the perpendicular component, you will just have field lines coming in from the bottom face and exiting from the top face. So what do I mean by this? That zero flux, B dot dA, surface integral is equal to 0. It means that these field lines, whatever be the number of field lines coming in, will be equal to the number of field lines going out. So B perpendicular above will be equal to B perpendicular below. Of course, uh, here it is going into the surface and here it is exiting the surface. We're just looking at the values over there. So the normal component passes continuously. So there is no change in the normal component. But what about the parallel component? These two parallel line strokes that we have written. This is the parallel component of the magnetic field. We shall use the idea of an Amperian loop. Here we are. You have drawn a square loop, square Amperian loop intersecting this sheet. This is a copper sheet. try to follow the physical diagram carefully. Current is passing from this edge and going towards that edge of this sheet. These arrows are current lines. You have drawn an Amperian loop which is square in shape. It could have been anything else, that doesn't matter, any other geometrical shape, but square is easy to understand as regards what we are doing now. Half of the loop is sticking above the sheet. This horizontal line indicates the sheet itself. Half of the loop is above this horizontal line, and the bottom half is below the horizontal line. So this square loop is above the line and below the line. Part of it is sticking up and part of it is sticking below. And it's got a height epsilon. This width is L. Going from left to right, the length is L, same here, and this height is epsilon. And make epsilon as small as possible. You're making a very small Amperian loop. And what does Ampere's law say in the integral form? That a closed surface integral B dot dl is equal to mu naught into I enclosed. So here's this square loop going round and round, and what is the current that is enclosing? The current that is enclosing is these arrows. How many arrows are passing through this loop, going from this way to that, going from this way to the other side? So from the front edge, which is closer to you, to the back edge, the current is going. So unit length will contain k current lines, k amount of current lines. Each line is there. So let's say you have lined up the current lines next to each other. So k amount of current lines are there in unit length. So in a length L, this is the width L, the amount of current that will be contained is k into L. K is the amount of current per unit length, as current, or you can even think of it as number of current lines per unit length. So if this length be L, then the amount of current will be k into L. And those current lines are passing through this loop. So this loop is enclosing KL amount of current. Okay, so that is the I enclosed, line current density. Fine. Now, let us see. Make epsilon as small as possible. Doesn't really matter. Now, this thing is going from left to right, B parallel. So there is a B parallel above and there is a B parallel below. Both are going in the same direction. Let us say from left to right. Okay, B dot dl is, we'll now have to carry out 4 integrals. B parallel above this plane, dot dl, this is the length L, will give you B parallel above into L. Okay, so this is the first term. Second term, you have B parallel above here and you have B parallel below here, both going from left to right. But this thing is perpendicular to both. That's why I said it's easier to understand when I draw a square loop. So when I take the dot product of B dot dl for this arm, both the parallel component, parallel to the sheet, both above and below will be perpendicular to this vertical arm, this downward path. So the dot product of along this path, B dot dl will be equal to 0. So this part of the integral contributes nothing. Then below, B parallel below is going from left to right, but this path is going from right to left. Therefore, between the two of them, they are subtending an angle of 180 degrees. If that is so, the dot product will give you B parallel below, dotted with L, L going from right to left, L cos of 180 degree, that will contribute this minus sign. And then when you go from this to this, bottom to the top, you will again have the field lines are going from left to right, and this path is going from bottom to top. So the line integral for this last bit over here will be 0 because the field lines and that path are perpendicular to each other. So basically, B parallel above L minus B parallel below into L will be equal to B dot dl integral. So this part will contribute 0, this part will contribute 0 to the path integral. This part will contribute B parallel above into L, and this part will contribute minus B parallel below into L. And what is B dot dl loop integral? Mu naught into KL. So mu naught into KL is equal to this thing. The L here, the L here, and the L here will cancel. And you will have B parallel above minus B parallel below is equal to mu naught into K. And so the parallel component changes discontinuously. I think if you look at the electric field scenario, you will see it is uh, completely different. There, the perpendicular component changes discontinuously, the parallel component changes continuously. E perpendicular and E parallel. Look up the notes that have been supplied to you or the lecture recording. So that is what you will get to see. This is, as I said, magnetism and electrostatic, electricity and magnetism. I should no longer use the word statics anywhere now. Electricity and magnetism are head and tail of the same coin. Okay, one last point to discuss on this slide is that vector potential divergence of B is equal to 0 and divergence of the curl of A is equal to 0. This is divergence of B is equal to 0 is a physical statement. It comes from the physics of electromagnetic theory. Divergence of B is equal to 0. A divergence of the curl of A is equal to 0 is a mathematical statement. Fine. So B can be written as the curl of a vector potential. And since it's a potential, just I'm making the statement, but it's very easy to show. In fact, it's far easier than this. I mean, you can check up your notes on electrostatics where we have done something similar for the electric field. And just doing something over here that the potential, the vector potential above and below will be the same. Anyway, so let me just go back to this page here, page number 120. It contains a whole lot of very important information. This correction of Maxwell is a very important contribution. It would not have been possible if Maxwell had not accounted for time variation, explicit time variation of the change of the charges or the current. Unsteady current. Unsteady current will give rise to a correction to the steady Ampere equation. This is the steady Ampere equation. Curl of B is equal to mu naught J. Up to that, you have Ampere's condition for a steady current. When you have an unsteady current, then it will give rise to an unsteadiness in the electric field, and that will have to be added, epsilon naught del T of E. Okay, I shall stop the sharing here and move on to a new set of slides. Note that this is page 120 where we end. Hereafter, page 121 to page 126, we discussed polarization already. We discussed electric polarization, all those D and P polarization, all those business. I just skipped that. Now what we shall do is we will move on to page 127 after this. I'll stop the sharing of. Just a minute, please. Just please bear with me. Please give me a minute. Thank you. Please confirm that you can see the presentation. Can anybody please confirm?
Yes, sir.
Yes, sir.
Okay, thank you very much. Please mute your mic. Okay, so as I said, we ended that Maxwell business and all that at page number 120 and 120A. Now we shall fast forward to page 127. We have discussed polarization already, 121 to 126. Here we have magnetic fields in matter. Just like in polarization, we talked about electric field in material medium where you have polarization, charges in insulators, dielectrics, where charges are bound. They are not free to move. So it is that what happens to magnetic fields in matter. Let us see now. Magnetism is the consequence of many current loops on an atomic scale. Just a while ago, I discussed the Maxwell equations. Nowhere in any of the Maxwell equations did he discover anything like a north pole or a south pole of a magnet. All of magnetism is the outcome of a physical element of charge known as electricity. Um, Maybe I'll just touch upon a very important point. I'm sorry. While we discussed all that, you see, the thing is that I told you a while ago that electricity and magnetism are two faces of the same coin. So suppose you've tossed a coin and the coin has landed and it, let us say, shows head. As soon as you see head on one face, you immediately know that the other face, what the other face is like. It has to be tail, and you know what a tail is like. I'm talking about coin of our country, India, with the Ashok stamp on one side and the coin value on the other. So the Ashok stamp on one side is traditionally called head, and the number side is called tail. Okay, so if you're familiar with the coin, you would know if you see one face, you'll immediately know the other face. So there is no special need for you to be supplied the information two times. You know the one, you will know the other. Something like that happens in nature also. Because you see, nature has got her own economics. Economics meaning that you apply your resources, economics in the sense that nature would apply her resources carefully. So if magnetism and electricity are tied to each other through a set of laws that are expressed in mathematical language through of the mathematical language of the Maxwell equations, then if you have the one, you will have the other. Divergence of E is equal to rho by epsilon naught. Divergence of B is equal to 0. Curl of E is equal to minus del T of B. And curl of B is equal to mu naught J plus epsilon naught mu naught del T of E. Nowhere on the right hand side you'll see anything but rho and J as sources of both electricity and magnetism. What is rho? Rho is charges. J is the current cross-sectional current density. So if nature gives you electricity, the physical element of electricity, from that, through the Maxwell equations, you'll immediately get both electricity, of course, you will get, and the physical element of electricity is the charge. So from that, you'll also get magnetism. Nature doesn't have to give you two sources at the same time if one is enough to produce two, the two vector fields, electricity and magnetism. So that is what we have. So magnetism is a consequence of many current loops on an atomic scale. You will say that, okay, I have given you a bar magnet. It will attract iron objects, all that sort of a thing. It will stick to your fridge door. You would have seen bar magnets, most of you, I think all of you. So the question is that you will say that what current is flowing in this thing? I'm just holding the bar magnet in my hand. There is no battery lined up as a part of a circuit in this in this bar magnet. So what is giving rise to its magnetism? Here's the answer. Magnetism is the consequence of magnetism of a bar magnet, let us say, is a consequence of many current loops on an atomic scale. What do we mean by that? Let us try to understand that. You have an electric dipole moment. I'm talking about electric dipole moment P. What is the dipole going to look like? The dipole will look like a plus end and a minus end. That is the dipole. The plus and the minus ends are separated by a displacement d. And so the electric dipole moment P will be given by Q into the displacement vector from the negative end to the positive end. That is the value of the electric dipole moment as in P. What about a magnetic dipole moment, as in M? This M is not to be confused with mass M that is usually used in physics. This is M vector, whereas the mass M that you write is a scalar. Be careful about making that distinction. So you would say that I'm talking about old physics, not the, I mean, pre-Ampere or Maxwell and or Oersted kind of physics. So just like you have an electric dipole with a plus end and a minus end, you have a magnetic dipole with a north pole and a south pole. And the magnetic dipole moment dipole should be thought of something like this. No, said Ampere. This model, a north pole and a south pole and a dipole moment, was given by Dr. I think his name was Edwin or Edward, whatever, Dr. Gilbert. Anyway, I mean, he was a doctor, medical doctor. I mean, he was the personal physician of Queen Elizabeth I of England, not the present Elizabeth, the one that lived 400 or 500 years ago. So that this thing, this was the Dr. Gilbert's idea of a magnetic dipole. Ampere overturned it. A magnetic dipole is not like this. A magnetic dipole will reflect this fact that it is the consequence of a mini current loop on an atomic scale. Here it is. You have a current loop going round and round. I is the current. The magnetic dipole will look like this. An electric dipole will look like this. Two black dots at the end of a rod. A magnetic dipole will look like a circle with an arrow sticking above. That is the correct way to think of a magnetic dipole, not like this. So this is Ampere's model of a magnetic dipole moment. A magnetic dipole. So now you'll say, okay, fine, that is all right. When magnetism is the consequence of mini current loops on an atomic scale, what atomic scale are we talking about? And what mini current loop do you have on an atom? Indeed, we do. So what is the mini current loop? Think of an electron going round and round a nucleus. So the electron is a charge particle. So charge is going round and round. What is a current? Current is charge flow per unit time. So if the electron makes one closed circuit, one completes one revolution, it takes one time period of revolution, capital T. So the charge flow per unit time will be the charge of the electron divided by the time period. But of course, don't forget something. Current is not the flow of an electron, but the flow of a positive charge. So instead of an electron going round and round, you should imagine it as an equivalent positive charge going round and round in the opposite direction. That is the loop current on an atomic scale. But we will come to that discussion later. For the time being, we will just apply Biot-Savart's law. Magnetic field due to a current carrying loop. In the last class, you remember my telling you that there was a tutorial that was given to you, question number 10. I just stated the answer, but we did not solve it. Here's the derivation of how to find a current carrying loop. Earlier, by the application of the Biot-Savart law, we were able to find the magnetic field due to a long straight conductor, an infinitely long wire. But instead of an infinitely long wire, we now have a closed circular loop wire carrying a current. What will be the magnetic field due to the current carrying loop? Of course, we will have to apply the Biot-Savart law, which I have discussed already. This is the Biot-Savart law, mu naught by 4 pi into I by r squared dl cross r cap. Now let us first try to understand this diagram. Here we are. You have a current going round and round. This is the axis. Going round and round in a disk. This is the center of the, going round and round in a loop, a closed circular path. This is the center of the circle. A line is passing perpendicular to the plane containing the circle along the direction x, let us say. Okay, now let us see. This thing, this is the disk. You apply the right-hand rule if you want to, but you don't have to right now. So this current, you're looking at the disk from the back part. So this is the current that is going. So the current is going up this way, coming out of the plane of the paper towards you, going down here, and then entering the plane of the paper here. So if you are, it's like that you're looking at the disk from behind at an oblique angle. So that is how you should see it. You're looking at it from behind at an oblique angle. So that is the direction of the current. If that be the direction of the current, then by the right-hand rule, you would immediately say that this going from left to right should be the direction of the magnetic field. But we'll come to that point later. Anyway, so let's see now what happens. What is the Biot-Savart law telling you? Let's see, from the center up to this point, the perpendicular distance is x. You take a small section dl here, and similarly a mirror image of dl down here. At this point, the current is coming out. Once again, I'm stressing, at this point, the current is coming out of the plane of the paper and pointing towards you. And at this point, the current is going into the plane of the paper and going inside. You're looking at this disk from behind, slightly at an incline from behind. Fine. Now, from this point dl to this point of observation, there's a vector displacement r here. And the unit vector along this direction is r cap, as in here. Okay, and this is your dl. So at this point, so this is a straight line that is going, and thereafter it is tracing this green colored line. This green colored line here is an extension of this straight line. Okay, so let us see now at this point what will be the direction of the magnetic field due to this small section here, dl. dl is coming out towards you. This is r vector. So take the cross product of this thing. R vector will have r cap here. That will be this thing. So this is going this way. This is coming out towards you. Both are contained on the same plane. Therefore, first vector swept onto the second vector. This will be the direction. This purple lines, I hope you are able to see the purple color. This will be the direction of dB. Okay. Now here, dl is going inside the plane of the paper at this point, going inside the plane of the paper. And just a minute, please. Sorry. Yeah. So here dl is going inside the plane of the paper, and this is the vector r, which will give you the direction of r cap. So r cap is pointing this way, dl is going inside, and so dl swept onto r cap will give you this dB direction. This is simple law of cross products. What is the direction of the vector field, that vector product field, direction of the product vector. Now what I do is I decompose this vector and this vector into its vertical component, as in these two red lines. For this vector, this is the vertical component. For this vector, this is the vertical downward component. And the horizontal component, this is the horizontal component. And for this is also the horizontal component. I've written something over here. Only the component along the axis survives. This green component along the axis of the circle will survive. And this red vector and this red vector, they will cancel each other out. Okay. Now, if this is dB, then this red vector will be dB cos theta. And if this is dB, then this green vector will be dB sine theta. Okay. Now, what is the value of sine theta? Let us see. This is angle theta. By definition, sine is perpendicular upon hypotenuse. I hope you are able to understand that if this angle is theta, then this angle will also be theta. And therefore, these two angles will also be theta. This and this are mirror image of each other. Let us just worry about this thing. If I were to take this thing and coincide, the blue line coincides with the red line, then this thing will coincide with the green line. If this thing is shifted a little by an angle theta, this will also shift by the same angle theta. These two are 90 degrees to each other. This dB and this vector r, they must be, because this is according to the law of cross product of vectors. So this angle is theta, and this angle theta, this angle is theta, this angle is theta, this angle is theta. Okay, so what is sine theta? Sine theta is perpendicular upon hypotenuse a by r. Sine theta is equal to a by r. Now, what about the magnitude of this thing? Let us now worry about that. Mu naught I by 4 pi r squared is fine. Then dl, magnitude of dl cross r cap. So magnitude of r cap is 1, dl into r cap. And then the only component that will survive will be the sine theta component. So there you have sine theta. You put it here. So that is the only surviving component that you have. Next is, we are writing sine theta as a by r. Follow carefully. And the integral will be over this loop only. B will be equal to integral of dB. Now let us see, mu naught I by 4 pi r squared is same, a by r is same. And this loop completely taken all around will give you 2 pi a. Integral of dl over this closed loop will give you 2 pi a. I could do it in two ways. I've done it in one way. One way is to only the component along the axis survives. If the component along the axis survives, then I could have written this component is reinforced by contribution from this dB and this dB. Then I should have written 2 over here. But if I had written 2 over here, then already having accounted for contributions from both sides, I could only carry out the integral over half the circle, and I would have got pi a. So here, instead, I have kept 1 into this, and just kept the component of one vector, and then I have integrated over the full loop 2 pi a. And then you just gather all the terms, a bit of cancellation, if at all. So you have got mu naught I by 2 pi and 4 pi will cancel to give you a 2 here. R squared and R will give you R cubed. A into A will give you A squared. And what is R? R squared is equal to A squared plus X squared. So R raised to 3 will be A squared plus X squared square rooted over and then raised to 3. So that is what you have. That is the magnetic field B, and that magnetic field B will be directed along this axis all the time. So when x goes to infinity, this thing will be divided by a very large number and B will be 0. So along the axis, the magnetic field is weakening. If you go this way to infinity, the magnetic field will be 0. And here at the center of the axis, when x is equal to 0, you put x is equal to 0 over here, and you will get B is equal to mu naught I A squared by 2 A raised to 3. A squared raised to 3 halves will give you A raised to 3. So B will be equal to mu naught I by 2A. So that is what you get here. So this is the magnetic field due to a current carrying loop. Let us just try to understand this thing. If the current had been straight, follow. We discussed this thing earlier. If the current had been straight, the magnetic field would have gone round and round. If the current is now going round and round, then the magnetic field is straight along the axis. So in both cases, the right-hand rule applies. Stick your thumb, take your right hand, stick your thumb perpendicular to your fingers, curl your fingers. One scenario. Thumb is tracing the direction of the current. The fingers are tracing the direction of the magnetic field. Magnetic fields are going circularly around the straight line current. Opposite scenario, current is direct along the curling of the fingers. Then in that case, the magnetic field will be sticking upwards straight like this. And this is the scenario that you have. Current is going like this. As in here, the current is going like this, and this is the direction of the magnetic field, and so this is, the current is going like this, and that will be the magnetic dipole. So this picture is quantified through this discussion, magnetic field due to a current carrying loop. But then I have touched upon something, general magnetism in a bar magnet. A bar magnet doesn't have any current or anything passing through it, external current, that is. You haven't applied a battery across the ends of a bar magnet. So the question is that how does a bar magnet naturally display magnetism? Initial supposition was that there's a north pole and a south pole and all that business, but now, no. You have Ampere's model. This is what it is. And so where is this current coming from? They are coming from mini current loops on an atomic scale. So we shall now look at that with the help of this, with the help of the understanding that we have derived from this discussion. We go to current loop formed by an electron. Let us see how. An electron going around a nucleus will behave like a current loop. So here we are. This is the nucleus here, probably somewhere there at this point. This is the electron going round and round. Area is pi r squared. If the radius of the orbit of the electron is r, then the area is pi r squared. Current is E by T. Be a little careful. Although I'm writing E, this E minus represents an electron, but current must be seen as the flow of a positive charge. So current is actually an imaginary flow of a positive charge in the opposite direction. If this is the electron, is the arrow is directed this way, the electron arrow is directed this way, then the actual current arrow will be directed in the opposite way, manner. So current is equal to E by T. What is capital T? Capital T is the time period of the revolution. Current is equal to E by T. So current is the flow of a certain amount of charge in a certain time window. So in T time, capital T time, E amount of charge would have flown past you. You're sitting somewhere here and observing the charge to go around. So current I will be E divided by the time period. And what is time period? Time taken to complete a full revolution. And what is the path in a full revolution? 2 pi r is the circumference. That's the path divided by the speed with which the electron is traveling, 2 pi r by v. So basically time period is 2 pi r by v, and so that is what we put. So the v comes up here, ev by 2 pi r. Magnetic dipole moment, just like electric dipole moment is defined as charge into displacement, the magnetic dipole moment is defined as, be a little careful, don't confuse this m with mass or something like that, although it's all too common to write m as mass as m in physics, but here's m vector. Magnetic dipole moment is scalar value of the current multiplied by the area of the loop, and area is a vector. Don't forget that. Area is also a vector, area of the loop. So m, I'm now just looking at the scalar values of it. M is equal to this, m is written, I tried to write it slightly differently than the way I would write a normal m. M is equal to I into A. Area is EV by, I is I is EV by 2 pi r, this thing, and area is pi r squared. Area of the loop enclosed by the orbit, that is area of the loop, pi r squared. So all this pi business will cancel, this pi and this pi will cancel, this r squared and this r will cancel to give you r, and so m, the magnetic moment, is EVR by 2. Okay, but there's a slight problem with this formula. What is the problem? The problem is that the V and R are not known a priori. I mean, what is the velocity of an electron in a magnetic loop? What is the radius of the loop? Orbital. What is the velocity of the electron in an orbital loop? What is the radius of the loop? Those things are not very easy to find out. E, the charge of an electron, is known, but what about these two? We'll have to eliminate these two things, the product VR, using something else. And here comes a very important thing from a completely different domain of physics, atomic physics or quantum mechanics. I've written something over here. You know the planetary model of the atom, where the atom is supposed to have a positively charged nucleus, just like the sun is situated at the center. Sun is the nucleus, so to speak, of the solar system, situated at the center of the solar system, and the electrons are like the planets going around the sun. Okay, but there's a slight problem with this whole business, which is not there in planetary physics, is that the electron is a charged particle. And if it is going round and round, then it must be accelerating. Why should it be accelerating? Because that is what Newton's first law states. The electron is a particle, charged or otherwise, whatever. And so any object, look, let's recall Newton's first law. An object tends to maintain its state of rest or uniform motion along a straight line, unless an external force acts on it. So here the object, namely our electron, is not executing motion along a straight line. It is going in a circle. Therefore, a force must be acting on it. And if there's a force acting on the electron, then the electron must be accelerating. That's also there for planets like our Earth. At this very moment, the Earth is accelerating, except that the acceleration is not so much on the speed, but on the direction. The direction is changing. The Earth is going in a circular orbit, nearly circular orbit, slightly elliptical. Okay, so if the electron is accelerating, there's a big problem with that, because it's a charged particle. And there's a theory of classical electrodynamics, which I haven't touched upon in this course. This is just a beginner's course. And classical electrodynamics says that a charged particle must accelerate. An accelerating charged particle must radiate energy. And if it is radiating energy, it is losing energy. And if it is losing energy, then it will not be able to continue on this thing. It will continue spiraling in and fall into the center. The electron will just spiral in, Upon having lost energy, this conservation of energy allows the electron to maintain its closed loop. Sorry, someone want, what is the matter? So the conservation is allowing the electron to maintain its conservation of energy allows the electron to maintain its closed loop. For instance, if you look at a pendulum will, if the pendulum were not to undergo damping or dissipation of energy, it would have maintained its amplitude constant forever, but that doesn't happen. If you oscillate a pendulum, however good and smooth that pendulum might be, after certain elapse of time, long enough, let's say, you will see that the oscillation dies out. So the same thing should happen for an electron also. The electron should, instead of oscillating, it is going round and round in circle and it will collapse at the center. But that doesn't happen. So why is it not happening, even though the electron is a charged particle and accelerating? Niels Bohr doesn't try to answer that question, but he says that let's just say that there are special designated orbits where the electron will not obey this behavior of charged particles, that even if they accelerate, they will lose energy, radiate away energy. So there are some designated orbits where the electron will not obey this behavior. And so if it doesn't, then what is the, I mean, you can very well say that there are some orbits where the electron doesn't obey this behavior. What are those orbits? What are the defining properties of those orbits? Here's the defining property of those orbits, that this quantity, MVR, this M and this M are not to be confused. This M is the magnetic dipole moment M, and this M with a subscript E is the mass of the electron. This MEVR is the magnitude of the angular momentum of the electron. The electron is going round and round. It has got an angular momentum. In the most general sense, angular momentum is written as mass into R cross V. And so if this is R and this is V, and if they are perpendicular to each other, and R cross V will be magnitude of R times magnitude of V times sine of 90 degree, which is 1, times the direction. The direction will, of course, be above, sticking up. Let's not worry about the direction now. We'll just look at this thing. Mass into V into R is equal to, so that's the angle, angular momentum, Bohr postulate. And this is something that you must have read in your school physics, Bohr model of the hydrogen atom. Two properties, two equations he said, one on the angular momentum and the other on the energy, that the energy of transition from one orbit to another will be equal to h nu. H nu as in the photon transfer energy of coming from Planck's formula. I'm not getting into that one, but this is important. Me into Vr is equal to nh by 2 pi. What is nh by 2 pi? H is Planck's constant. 2 pi is your old friend 2 pi. 2 pi into r, actually. This 2 pi into r will give you the full circumference, 2 pi r. And n is a quantum number. 1, 2, 3. You will not have 1.3 or 2.6 or 3.2 and nothing like that. You'll just have integral numbers, 1, 2, 3, like that. So any electron orbit that respects this condition, that the angular momentum of the electron in that orbit will be an integral multiple of h upon 2 pi. Any electron orbit respecting that condition, Bohr postulate. Postulate means a technical educated guess, not a random guess. So a technical guess. So will obey, will not radiate energy. So we shall use that thing. Bohr's postulate turned out to be correct, at least experimentally supported. So we'll put our faith in this thing and we shall use this thing. What shall we do? We shall substitute this VR from this formula. What is VR? VR is equal to NH by 2 pi into ME. And so M is equal to E by 2, and then VR is NH by 2 pi ME. H by 2 pi in shorthand is written as H cross. H cross is equal to H by 2 pi. Let me show it here, H by 2 pi. Okay, so it will be E into H cross. There's an N up here, then 2 times ME. You look at this package, E, H cross, 2 times ME, they're all fundamental constants. E is the charge of the electron, everywhere fixed in the universe. M is the mass of the electron. everywhere fixed in the universe. H is Planck's constant, everywhere fixed in the universe. So everything. And n is just a number, 1, 2, 3, etc. We just look at n equal to 1. So the magnetic moment of an electron going round and round will be an integral multiple of this basic minimum package. Here you can see the idea of the quantum coming in. And this thing is known as the Bohr magneton. Bohr as in Niels Bohr, magneton. What is a magneton? The minimum irreducible quantum of magnetic moment. Just like what is the minimum irreducible quantity of a charge? You call it the electron. Minimum irreducible of the quantum of light, photon. Photo as in light, and so the quantum particle of light is a photon. Similarly, the quantum particle of charge is an electron. And here, the quantum, I'm not using the word particle over here, the quantum, minimum quantum of a dipole moment, magnetic dipole moment here is a magnetic dipole moment. The minimum irreducible quantum of a magnetic dipole moment is known as the Bohr magneton, EH crossed by 2 times ME. Anyway, so with that, I should stop here. Time is up. I just would like to tell you a few things before I end the session now. First of all, I'll stop sharing this thing. Before I end the session now, there is a tutorial this afternoon. You will be sent all the material, I mean the tutorial sheet and the link that is there. And this Friday is a holiday, in case you are not aware of that fact. This Friday is a holiday because of Guru Nanak's Jayanti. And so we shall not have our class this Friday, but this afternoon we shall have the tutorial. So that is the point I would like to make. I'll stop the recording also. Meanwhile, if you have any question to ask me, please do so. Otherwise, we may